All right, welcome to The Explainer. Today, we're stepping beyond the familiar world of rows and columns. We're going to dive into a technology built from the ground up to handle something that, well, gives traditional databases a real headache: connections. We're talking about graph databases.
So let's kick things off with a paradox, one you've probably run into yourselves. Relational databases, right? The name says it all. But ironically, they can really struggle when you ask them to explore deep, complex relationships in your data. As you start connecting the dots further and further apart, you run into this massive performance bottleneck, a little something we'll call the join pain problem.
And at the heart of this issue is a totally different way of thinking. Relational databases are fantastic at one thing: storing data in tidy tables. But graph databases, they treat the relationships between your data points as first-class citizens, just as important as the data itself. And that one simple idea, that shift in focus, is what lets them solve problems that bring other systems to a grinding halt.
Now, this join pain, it isn't just some theoretical inconvenience. The performance cost is very real, you could measure it, and frankly, it's staggering, especially as your queries get more and more complex.
Okay, so check this out. This table tells a really dramatic story. It's from a benchmark test looking for friends of friends in a social network of 1 million people. At 2 degrees of separation, friends of friends, they're both super fast, no problem. But look what happens when you go just one step deeper. The relational database suddenly takes over 30 seconds, while the graph database is still flying. And by the time you ask for friends 5 levels out, the relational query just gives up. It couldn't even finish.
And this chart just hammers the point home. Let's zoom in on that depth 4 query. The relational database took over 1,500 seconds. That's more than 25 minutes for one query. The graph database? It answered the exact same question in just over a second. That right there is the difference between a real-time application and an overnight batch job.
So you have to be asking, how is that even possible? Well, this incredible speed advantage doesn't just come from a magic algorithm. It starts way earlier, with a much more natural, more flexible way to model your data. A way that, honestly, mirrors how we all think. Think about it. When you and your team are brainstorming a system, what do? You go to the whiteboard, right? You draw circles or boxes for your entities, your users, your servers, your applications, and then you draw lines connecting them. It's simple, it's visual, everyone gets it. But then comes the tough part. To get that beautiful, simple whiteboard drawing into a relational database, you have to twist it and force it into a rigid schema. You start adding foreign keys everywhere, and even worse, you create these extra tables, join tables, whose only job in life is to connect your other tables. The clarity of your original idea just gets lost in translation. With a graph database, though, there's no painful translation. You're not forcing a square peg into a round hole. You take that whiteboard model and you just enrich it. The circles become nodes, the lines become relationships, the structure you drew is the structure you build. What you sketch is what you store. It's that simple.
Okay, so we've covered the what. Let's get into the how. How does this intuitive model deliver that crazy speed we saw earlier? Well, the secret sauce is an architectural concept called native graph processing.
The key idea here is something called index-free adjacency. So instead of having to look up connections in a massive global index every single time, each node in a native graph database physically stores direct pointers, like actual memory addresses, to its neighbors. Each node knows exactly where its connected nodes and relationships live on the disk.
So what does this mean? It means when you run a query, the database isn't doing a big, slow index search. It's just following these pointers, hopping from one node to the next. And this is the crucial part. The performance of your query is determined by how much of the graph you actually explore, not by the total size of the database. This is how you stay in real time, even when your dataset grows to billions of nodes.
But this native structure does way more than just make your queries fast. This is where it gets really powerful for us as data scientists. It transforms the database itself from just a storage system into a high-performance engine for graph analytics and algorithms.
So you can take a core network theory concept like triadic closure, the idea that if you and I have a friend in common, we're more likely to become friends ourselves. Graph databases lets you operationalize that idea directly. You can run link prediction algorithms right inside the database to power things like a real-time recommendation engine without having to ETL all your data out to some other system.
Or think about classic pathfinding algorithms like Dijkstra's. Running this inside the database is a total game changer.
the algorithm is literally traversing the native graph structure, which makes it incredibly fast and efficient for any kind of logistics, network routing, or optimization problem you can throw at it.
And these capabilities, they directly power some of the most complex and valuable data science applications out there today. We're talking about uncovering sophisticated fraud rings by spotting weird connection patterns, optimizing massive supply chains on the fly, and analyzing huge social networks at scale.
So really, at the end of the day, it's about this. The real world is a messy, richly interconnected web. Graph databases don't try to fight that, they're built to embrace it. And by doing that, they give you not just a more intuitive model and way faster queries, but a powerful platform for doing real graph science.
Which brings me to the final question, the one for you to think about. In those complex, interconnected datasets you work with every single day, what valuable patterns, what hidden relationships, what game-changing insights are you missing simply because you're forced to look at your world through the lens of a table?